So this is the Unit 9 Day 1 classwork, and you should probably try to work through these problems first and then check your answers with the key. And if you have questions on any of the problems, that would be the time to watch these videos. So we're going to start by doing the limit as x approaches 0 from the left. That's number 1. So here's 0, and I'm going to approach 0 from the left. So as I come from the left, I'm approaching this y value right here, and that y value seems to be maybe 5. And in problem 2, we approach 0 from the right, and I'm still approaching 5. And because the left limit equals the right limit, the limit as x approaches 0 equals 5. And number 4, the limit as x approaches 3 from the left. So 3, 1, 2, 3. Let's switch color. So here's 3. As I approach 3 from the left, I'm approaching y value 2. And as I approach 3 from the right, I need to go to the right of 3 and get closer and closer to 3. I'm approaching the y value of negative 2. So the limit of f of x as x approaches 3 does not exist because the left limit is not the same as the right limit. Does not exist. And this seems to be the exact same question. No, this is negative 3. So now we're doing negative 3. 1, 2, negative 3. So the limit as x approaches negative 3, it's the same on the left, and it is on the right, it's negative 1. So this one's negative 1. However, f of negative 3, they're looking for the defined value. They're looking for the filled in hole. So you need to go all the way down here to negative 4. So problem 9 says, is f continuous at negative 3? Well, the first question in is it continuous is that value defined? And yes, it's defined at negative 4. The second question is, does the limit exist? And yes, the limit exists at negative 1. But the third question is the defined value equal to the limit? And it's not. So we would say f is not continuous at negative 3 because of part 3 of the continuity definition. Number 10, we want the limit as x approaches negative 4, so that's over here. And I can approach negative 4 from the left. I can approach it from the right. Either way, I get the answer 1. In 11, is f continuous at 3? So here's 3, and we remember that at 3, the limit does not exist. So this is not continuous because of part 2 of the continuity definition. And in 12, is f continuous at 4? So here's 4. F is continuous at 4 because in part 1, f of 4 is defined. In part 2, the limit exists because the limit from the left is the same as the limit from the right. And in part 3, the defined value is equal to the limit. So this one is yes. All right, next graph. What is the domain of f? So we read the domain of f from the left to the right. We need to start over here at negative 6 and include it because of the filled in dot. And we go to our first break in the graph at negative 4. There is no value at negative 4. They're both holes, so we have to leave out the negative 4. And then at negative 4 we pick up again to negative 2. It is defined at negative 2, so we don't have to leave that out. And then we go to 0. It is defined at 0. We don't have to leave that out. But we get up here to 2. We do have to leave 2 out. So we need negative 4 to 2. And then after 2, we're good until we get to 5. Then we have another hole. So we're going to go from positive 2 to 5. Leave out the 5. And then we keep going until 6. Another square bracket to include the 6. The range, however, starts all the way down here at negative infinity. It keeps going up until 1, and then after 1 it picks up again right here. Looks like maybe we would have to leave this value out of the range, but nope, it's covered over here. So we keep going all the way up to positive infinity. So the range is simply negative infinity to positive infinity. Alright, 31 and 32, we're looking for the defined values, the filled in values. So f of negative 6 it's all the way back here. It's positive 2. And f of negative 4, this one's a whole, this one's a whole, so there's no defined value. So we say f of negative 4 is undefined. F of negative 2, we don't want the whole, we want the filled in value, so that's 2. And then f of 6 is this last point on the graph, and that would be 0. Now we're back to limits. The limit as x approaches negative 4 from the left. So 0, 2, here's negative 4. As we approach negative 4 from the left, we're approaching this hole right here, and that one has a y value of 4. So this is 4. The limit as x approaches negative 4 from the right. So here's negative 4 again. As we approach it from the right, we're approaching this hole, and so that limit is negative 2. Negative 2 now. So the limit as x approaches negative 2 from the left, that's over here, also negative 2. And here's negative 2 again. We're going to approach negative 2 from the right, and it's this value here, positive 2. So the left-hand limit is negative 2, the right-hand limit is positive 2, so the limit as x approaches negative 2 will not exist, but that question is not asked. We're going to move on to positive 2. The limit as x approaches positive 2, which is right here, from the left is negative infinity, and the limit as x approaches 2 from the right. So from the right, looks like positive infinity. The limit as x approaches 0. So if we approach 0 from the left, we're up here at 4. If we approach 0 from the right, we're here at 1. So the two sides do not meet up. This does not exist. And then the limit as x approaches 2. Well, over here we did left-hand limit and right-hand limit. One was negative infinity and one was positive infinity, so this one does not exist. All right, then we're back to continuity. In 42, is f continuous at negative 2? No, because the limit does not exist. That's part 2. Is f continuous at negative 4, which is here? The first part of that definition is it defined at negative 4? It is not. So I'm going to say no because of part 1, even though part 2 is also not taken care of. And is f continuous at 0? So at 0 it is defined, but the limit does not exist, so I'm going to say no, part 2. And is f continuous at positive 2? So at positive 2, it's not defined, the limit also doesn't exist, but I'm going to stop at part 1. It's not defined, so I'm going to say no, part 1. Is f continuous at 4? So that's 2, 4 right here. Well, let's take a look. It's defined at that value. The limit is also equal to that value, so this one is yes, continuous. And is f continuous at 5? Well, it's not defined at that value. We have a hole, so we'll say no because of part 1. All right, let's turn the page on your classwork. On the next page, we have a lot of letters instead of having numbers, but we can answer these questions the same way. The first question is asking for a limit as x goes to infinity. So what this is really asking is for the end behavior of the function. And remember, if the function has a horizontal asymptote, then that is the end behavior. So as x goes to infinity, the y is approaching the horizontal asymptote, which is this value here, which is f. And the same thing happens on the left side. As x goes to negative infinity, we're also approaching the horizontal asymptote at f. The limit as x approaches a from the right. So here's a. As we approach from the right, we're approaching positive infinity. And as we approach a from the left, we seem to be approaching this hole right here, which has a y value perhaps of h. And let's see, because we don't have the same limit on the left and the right, we're going to say the limit as x approaches a does not exist. The limit as x approaches b from the right. So here's b. As we approach b from the right, looks like we're going to positive infinity. As we approach b from the left, looks like we're going to k. So the left does not equal the right, so the limit as x approaches b does not exist. The limit as x approaches c. C is right here at 0. So we approach from the left, we're approaching 0. We approach from the right, we're approaching 0. So that means the limit as x approaches c is 0. And the same thing happens at d. So here's d right at 0. As we approach from the left, we approach 0. As we come from the right, we approach 0. So this one's also 0. And now for g of a, we need the filled in value. So g of a, here's a. We're looking for a filled in value, but there's an asymptote and there's a hole. There's no filled in value, so we say this is undefined. For g of b, we do have a filled in value right here. It looks like that y value is I. And for g of 0, that's this filled in value right here, which is I. The limit as x approaches 0, we can approach 0 from the left, we can approach 0 from the right, but they're both also I. In the next section, we're supposed to be using these tables of values. Next class we will learn more analytically how to find these limits, but for today I graphed them on the calculator and I looked at the table of values. So let me just flip over to that for just a minute. So for 75, you can see your graph has a slant asymptote and a vertical asymptote, and we want to know the limit as x approaches -2. So if you look over here at the table of values, I'm approaching -2, and I do have an error at that actual value, but you can see as I approach from the left and as I approach from the right, I'm approaching a y value of -3. So using that table of values, I'm going to answer this as -3. In 76, we did the same thing. We're approaching 4. So as I approach from the left and as I approach from the right, you can see that the y value is going to be about 4. And the last problem, we want the limit as x approaches 1. And so as I approach from the left and as I approach from the right, we are zooming in on a y value of -1. And so -1 is our answer. And let's flip back to the last section. So we answered those previously. Find the limits by substitution. So we are going to substitute in the values and find our limits. By substituting in 0, I have 0 plus 1 over 0 plus 1, which gives me 1. In 4, I substitute 0. I get 2 minus 0 over 0 plus 4, which is 2 over 4, or 1/2. When I substitute 4 in problem 5, the problem I run into is I get 16 minus 16 over 4 minus 4, which is 0 over 0. So remember way back we said if you get 0 over 0, there is something you need to fix in this function. And today, that fix is just factoring. If I factor x out of the numerator, I have x minus 4 times x. And I also have x minus 4 in the denominator. So those cancel, giving me just the function x. So now if I plug 4 into that function, my final answer is 4. The same thing happens in problem 6. So you plug 3 in and you get 9 minus 9 over 9 minus 9, which is 0 over 0. And today we have the same fix. We're going to factor. So difference of squares, I get x minus 3 times x plus 3. And then in the denominator, I take out a common factor of x, and it's x times x minus 3. So cancel out your x minus 3's and plug 3 into the remaining factors. So I get 6 over 3, and my final answer is 2. In problem 7, plug in the 0, e to the 0 plus 1. Anything to the 0 is 1. So 1 plus 1 equals 2. And in problem 8, I have e to the 0 minus e to the negative 0, which is still 0, over 2. So subtracting these, you get 0 over 2, which is 0. And that's the end of your classwork. You should be able to use your classwork problems to help you solve your homework problems.